one of those days where a process that's been running perfectly, just humming along, suddenly goes completely off the rails? It could be anything, right? A car part, a patent application, it doesn't matter. Well, today we're going to put on our detective hats and investigate exactly that. And our main tool isn't a fingerprint kit, it's something called Statistical Process Control, or SPC. So let's get into it. This really is the million-dollar question, isn't it? 1 minute, everything's smooth sailing. The next, you're buried in defects, you're dealing with delays, and you've got unhappy customers. It just feels random, chaotic. But what if I told you it's not random at all? What if there are clues hidden in plain sight, just waiting for someone to connect the dots? All right, to kick off our investigation, we need to meet the main villain of our story. It's the hidden force behind pretty much every process problem out there: variation. It's the simple reason why no two things are ever exactly the same. And trust me, understanding it is the absolute key to cracking this case. Look, this is just a fundamental truth of the universe. Every single process, I don't care if it's a multi-million-dollar CNC machine or the person making your morning coffee, has some level of natural, built-in variability. You can't get rid of it completely. But, and this is a big but, you can understand it. And that understanding, that's our secret weapon. Okay, so here's where it gets really important. Not all variation is created equal. There are two very distinct types. First up, you've got common cause variation. You can think of this as the normal, predictable background noise of a process. It's just always there. But then you have special cause variation. This is the unexpected stuff, the jolt in the system. It's not noise, it's a signal. It's a massive clue that something specific has changed, and that is what we're hunting for. And this is exactly where our primary tool comes into play. SBC is designed to do one thing, and do it brilliantly. It listens to the voice of your process, and it tells you the exact moment that predictable background noise gets interrupted by an abnormal signal. It's all about separating those critical clues from the everyday noise. Every detective needs their go-to tool, right? For us, it's the SPC control chart. And this is way more than just a graph. This is our magnifying glass. It lets us see the behavior of a process over time in some seriously incredible detail. So take a look at this. You can think of this as our crime scene. Every single dot you see is a measurement taken over time. And yeah, at a glance, it might just look like a random collection of points, but I promise you, this chart is telling a story. It's a visual record of everything that happened in that process, the good and the bad. Now, here's how we bring some order to that chaos. Right in the middle, you have the center line. That's basically the historical average of the process. On either side of it, you've got the upper and lower control limits. Now, these are the critical boundaries, usually set about 3 standard deviations away from that average. They define the expected range of normal, common cause variation. Anything that happens between these lines is just the process doing its thing. So, how do you actually read the thing? It's surprisingly straightforward. If all the data points are just kind of bouncing around randomly inside those control limits, your process is considered in control. It's stable, it's predictable, life is good. But the moment a point jumps outside those limits, or if the points start forming a weird, non-random pattern inside the limits, that's the process screaming, "I'm out of control." It's telling you a special cause is there and you need to go investigate. Now, okay, so we've got our magnifying glass. We know what a healthy, stable process should look like. Now for the fun part. It's time to become expert pattern spotters and find those clues that tell us something's gone sideways. This right here is the mantra of the process detective. We're not just looking for those big, obvious points that fly outside the lines. No, we're on the hunt for anything that defies randomness. A trend, a shift, a weird cycle, any pattern at all is a piece of evidence. And here are some of the most common clues you'll see. The most obvious signal, kind of like the smoking gun, is a single point falling outside the control limits. But the clues can be way more subtle. For example, 6 points in a row all trending up, that's a clear signal that something is gradually changing. Maybe a tool is wearing down. Or how about 9 points all on one side of the center line? That tells you the entire process average has shifted. These rules turn us from just guessing into evidence-based investigators. Okay, we've found the evidence. The control chart has given us a solid clue, a trend, a shift, an outlier. Now comes the most critical part of the whole investigation, finding out who, or, what, is responsible. Because really, a clue is totally useless until it leads you to a suspect. The control chart is incredibly powerful. Don't get me wrong. It tells us that a problem exists and when it happened, but it can't tell us why. For that part, we've got to do some real detective work. So a fantastic tool for this is the cause and effect diagram. You might know it as a fishbone diagram. It gives us a really structured way to brainstorm our list of suspects. You start with the problem, the effect, at the head of the fish. Then you brainstorm all the possible causes and you group them into these classic categories known as the 6 M's. Was it the people, the machines, the methods, materials, measurements, or maybe the environment? And what's really cool is that you can start to connect the type of clue you found to the likely culprit. For example, if you see a big, sudden shift in the average, well, your suspect list might include a new operator, a major equipment failure, or maybe an incorrect setup. See a slow, steady trend? That points to things that change over time, like tooling that's gradually wearing down, or a slow change in the room temperature. See? We're narrowing the search. So here's the bottom line. The whole point of all this detective work isn't just about solving mysteries that already happened. It's about preventing future ones. SPC is all about being proactive. It's about catching that problem inside the process, saving money, cutting waste, and protecting your reputation before a bad product ever gets out the door. It's problem avoidance, not just problem solving. So far, we've seen how SPC helps us solve mysteries after the fact. But what if we could get ahead of the problem entirely? The future of quality control is shifting from investigation to prediction. Yeah, the days of somebody manually plotting points on a paper chart are pretty much over. We are diving headfirst into an era where data is collected in real time and analyzed automatically, letting our systems predict when a process is about to go out of control. And this is where the game is totally changing. Think about model-based definition, or MBD, as the master blueprint. It makes sure all your measurement data ties directly back to that original 3D design. Then you have Industry 4.0, which weaves this digital thread that connects every machine and sensor together so data just flows instantly. And finally, advanced analytics and AI can sift through that massive stream of data, spotting tiny patterns that can predict a problem long before a human ever could. And that really brings us to the final thought here. Statistical process control gave us the tools to be detectives, to investigate and to solve problems. But the next generation of these tools, they're aiming to turn us into prophets, giving us the ability to see a problem developing and to step in before it ever even happens. We're moving beyond quality control and into quality prediction. And that changes everything.